Hey everybody. Today we're doing more with partial fractions, dealing with the situation when the denominator has irreducible quadratic factors in it. We already know how to deal with the situation when the denominator factors entirely as a product of linear terms. Here's an example, and the idea is you're supposed to get one term in your partial fractions decomposition for every exponent there on the denominator. So the x minus 3 cubed in the denominator is going to give us three terms in the decomposition. Constant over x minus 3, constant over x minus 3 squared, and constant over x minus 3 cubed. Similarly, for the 5x plus 1 squared in the denominator, we get two terms in our partial fractions decomposition, because that exponent is 2. In every case, the numerator is just some unknown coefficient that we have to solve for. We solve for them by getting a common denominator on the right, and then equating the numerators once the denominators are the same. Unfortunately, not every polynomial can be factored into a product of the linear terms. Here's an example. Our denominator, x plus 1 times x squared plus 1, has an irreducible quadratic. X squared plus 1 can't be factored any further. The easiest way to see this, by the way, is using the discriminant of the quadratic formula, b squared minus 4ac. If b squared minus 4ac is less than 0, then the quadratic doesn't have any real roots, can't be factored any further, it's irreducible. For x squared plus 1, b is 0, a and c are both 1, so that discriminant b squared minus 4ac is negative 1. X squared plus 1 really is irreducible. So we would like to break this up with two terms, one with a denominator x plus 1, and the other with a denominator x squared plus 1. How do we do that? When you have an irreducible quadratic term in the denominator, the corresponding term in the partial fractions decomposition should have a linear numerator. Here's what I mean. The x squared plus 1 term has a numerator that is bx plus c. So that's just the general form for a line. Now, our procedure is exactly the same once we have that written down. We want to get a common denominator, equate the numerators, and then solve for the constants a, b, and c. So let's do it. On the right-hand side, I cross multiply to get a numerator of a times x squared plus 1 plus x plus 1 times bx plus c. And then I just keep the numerators the same. Since the denominators are the same, the numerators have to match up. Now, this has to be true for every single value of x, which means I can plug in convenient values of x if I like. Here, when I plug in x minus 1, the bx plus c term gets canceled. So I end up getting negative 3 plus 2 is 2a, and therefore a is negative a half. Unfortunately, there's not another convenient value that we can plug in to cancel out, for example, the a's and b's to be left with just c's. We're going to have to do some simultaneous solving. So let's take the equation we have and simplify it a tiny bit by using a equals negative 1/2. While we're at it, let's FOIL out x plus 1 times bx plus c. Here's the polynomial equation that we get. Now, in order for this to be true, the coefficients of x squared have to be the same on both sides, the coefficients of x have to be the same on both sides, and the constant terms have to be the same on both sides. So, looking just at the constants, on the left I have negative 4, on the right I have 1 minus 2c. Solving that, I get c as 5/2. Similarly, looking just at the x squared terms, I get 0 equals 1 minus 2b, or b is 1/2. Plugging those values into the partial fractions decomposition that I wrote previously, we get this. I don't love having fractions in the numerator of a fraction, so I'll neaten it up slightly to get negative 1 over 2 times x plus 1 plus x plus 5 over 2 times x squared plus 1. You have to be very careful when you're using partial fractions that you only do this procedure if you have a quadratic in the denominator that is irreducible, that can't be factored any further. You should not do partial fractions until the denominator is entirely factored. What about if you have powers of irreducible quadratics? Well, the procedure is very similar to when we had powers of linear terms. You get one term for every exponent of that irreducible quadratic, And you basically just count up the powers. So if the denominator is ax squared plus bx plus c all to the n, you get n terms whose denominators are ax squared plus bx plus c, ax squared plus bx plus c squared, and so on all the way up to ax squared plus bx plus c to the nth power. Let's do a few examples. X to the third minus 5x squared plus x over x squared times x plus 2 times x squared plus x plus 2 quantity squared. Here that last quadratic is irreducible. B squared minus 4ac is 1 minus 8, negative 7. That's less than 0, so it can't be factored anymore. We have 3 terms we have to deal with in the denominator. X squared, which is a linear term, x to the second power. So I get a over x plus b over x squared. The x plus 2 gives me c over x plus 2. And the x squared plus x plus 2 quantity squared gives me 2 terms, dx plus e over x squared plus x plus 2, and fx plus g over x squared plus x plus 2 quantity squared. Example 3. Here I have 2 quadratics in the denominator. X squared minus 2x plus 3 is irreducible because of that discriminant being negative, but the second one is not. X squared plus 2x plus 1 is x plus 1 quantity squared. I can't just plow ahead and do that with a term ax plus b over x squared plus 2x plus 1. I need to do it using the factored form. Now we can do our partial fractions decomposition. The x squared minus 2x plus 3 to the third gives me 3 terms in my decomposition, with exponents 1, 2, and 3. In each case, the numerator is going to be linear, for example, ax plus b. And then the x plus 1 squared term gives me 2 additional terms, g over x plus 1 and h over x plus 1 squared. One last example. X squared plus 4x plus 2 over x to the 7th minus x to the 3rd. I start by factoring the denominator, pulling out a common factor of x cubed, and then recognizing that x to the 4th minus 1 is a difference of squares. So I get x squared minus 1 times x squared plus 1. X squared minus 1 can be factored a little further. That's x minus 1 times x plus 1. Now everything is irreducible. I've got some linear terms, and I have the irreducible quadratic x squared plus 1. So the form of the partial fractions decomposition here is going to have 3 terms for the x cubed in the denominator, a over x plus b over x squared plus c over x cubed. It's going to have 1 term for the x minus 1 and 1 term for the x plus 1, c over x minus 1 and d over x plus 1. And then for the irreducible quadratic x squared plus 1, I have a linear term in the numerator, ex plus f, over that irreducible quadratic in the denominator, x squared plus 1.